So here's the state of affairs. So we started with DFA. Okay. And it can solve all regular expressions. Okay, so that's DFA. Then we went to context-free grammars, CFG. Okay. And it can solve strictly more than DFA. So something that DFA cannot solve with which context-free grammars can easily solve is equality. So this guy can solve, 0 to the n, 1 to the n. Okay, so that's CFG. And then we got Turing machines, okay, which correspond to algorithms, providing they're deciders, providing they always halt. So Turing machine deciders. Okay. And by Turing machine deciders, we now define what we mean by computable. So a problem is solvable, or we can write an algorithm to solve it, or that problem is computable. Okay, if some Turing machine decider can solve it, and we can solve all kinds of things. Basically, everything that we listed that cannot be solved by the CFG can be basically solved by deciders. So, repetition, W pound W, 0 to the n pound, 1 to the n pound, 0 to the n, triple equality, 0 to the n pound, 1 to the n squared, 0 to the n pound, 1 to the 2 to the n, half sum. Okay. All these problems, half sum, and we talked about graph problems like traveling salesman, connected components, networks. So all these problems can be solved by a Turing machine, by an algorithm. Finite answer to infinitely many questions. Okay. But there are all these fancy problems that we would like to solve, cannot be solved by Turing machines. So these are the decidable problems. Think of that as solvable by an algorithm that always halts. So then there are the recognizable problems. So problems that can be solved, but not necessarily always halting. So perhaps infinite looping. And AT and LTM, program verification, can be solved by UTM if you allow it to infinite loop. But okay, it's not practically useful. But for example, LTM is recognizable. Halt, the halting problem, is recognizable. You can build a machine that, when the program halts, will halt and say yes, but otherwise we don't know. It could infinite loop. Okay, so these are the recognizable problems. Not so practical that we cannot solve them without infinite loops. And then what about outside here? So this and this are all solved by Turing machines. So this is Turing machines. And then there are problems for which even there are Turing machines we cannot solve with Turing machine. We cannot solve with recognizers, even recognizers where we allow the possibility of infinite loop. So, for example, the complement of this language, LTM complement. So decide whether or not a program will fail on its input. Yes or no. So the complement of this. Okay. Now, to halt and say yes, you must be able to detect the infinite loop. We don't know how to detect infinite loops. Okay. This problem is just not even recognizable. So we say non-recognizable. Okay, and so that's the state of affairs for the theory of computing. What can we compute? What can we not compute? So on the left of this line, I'll put it in blue, we can compute important problems like halting, program verification, auto-grading. I'm sorry to tell you, it's such a sad way to call this lecture the punchline for the course. But I'm sorry to tell you, those problems are unsolvable. But on the positive light, now that we know what's not solvable and what's solvable, we can focus our energies on what's solvable. Okay. But it's important to be able to look at a problem and say, oh, well, that's not solvable. Go somewhere else. Do something else. Okay. And so that's what the focus of, let's say, the algorithms course will be, that follows this course, which is to take problems that we now know are solvable. So we forget about the ones that are unsolvable. And when I say forget about, I mean forget about. There's no point trying to solve them. The only value they have is in allowing us, via this concept of reduction, to prove that some other problem is unsolvable. And we focus on the solvable problems, and we try to build efficient algorithms to solve them. solvable problems. So that really is the next, phase in your path as a computer scientist. So let's now focus on solvable problems and see which ones can we solve efficiently and which ones can we not solve efficiently. And that leads us to the theory of NP completeness, which we will touch on next lecture, but we have really hit the punchline of this course. What is computable? What is not computable? By the way, from these non-computable things, you can always now go and derive even numbers. Just simple numbers are non-computable. You can prove. You can prove that. So for example, some number which we can define, but we cannot compute. So, important problems are not solvable. Lots of interesting and useful problems are solvable. How to solve them efficiently? Next time, checking out!